Hello everyone, welcome back to this online class. Today we are going to look at the method of separation of variables as used in solving partial differential equations. In particular, the PDE that we are going to solve is in cylindrical coordinates. It is given by the second partial derivative of u with respect to r twice plus 1 over r times partial u partial r plus 1 over r squared times the second partial derivative of u with respect to theta twice is equals to 0. So this is our PDE, and r ranges from 0 to L, theta ranges from 0 to 2 pi. Our boundary condition, that is at r is equals to 0, our solution should be finite. It should be a number that is different from infinity. It should be finite. And at the other end, when r is equals to L, our solution should be f of theta, where f is an arbitrary function. So how do we go about this kind of a problem? Using the method of separation of variables. Now the equation is in cylindrical coordinates. Look at our PDE. Our independent variables are r and theta, and our dependent variable is u. So from the equation, it is clear that u is a function of r and theta. So we are going to say that let u of r theta be equal to r capital times the capital theta. We are saying where the capital R is a function of the small r, and the capital theta is a function of the small theta. So we are separating the variables. Now, because this is the solution, or our solution should be in this form, it must satisfy the given PDE. So if this is our solution of the equation, then we expect it to satisfy the given equation. So I need to find the derivatives of u. So let's start. You can just say partial derivative of u with respect to r. So to differentiate that, you're going to keep any function of r to be constant, not r, but those of theta to be constant. So we differentiate r, that will be r prime times theta. Second derivative of u with respect to r twice. Again, this you differentiate r twice, keeping theta constant. And lastly, second derivative of u with respect to theta twice. Now we keep r constant, differentiate the theta twice. Remember, when we write r prime, it means derivative with respect to the small r. And when I write theta prime, is derivative with respect to the small theta. So theta double prime will be the second derivative with respect to theta. R double prime will be second derivative of r capital with respect to the small r. So now we know the partial derivatives. Let's go back to our equation and substitute those partial derivatives. So when you substitute them, we are going to get this. So you can say, therefore, our PDE will now be, let's start by replacing the second derivative. It will be r double prime theta plus, I can see this 1 over r. Then the first derivative of u with respect to r, that was r prime theta. Then I can see this 1 over r squared, r theta double prime is equals to 0. So remember, this is now a separable ODE. So let me bracket it. So this is a separable ODE. You can write it here. Separable ODE. So what do I do to separate the variables? I have to divide by, this is what you need to do. Divide by r squared. Is it r squared? No. We are dividing first of all by r times theta. What are we going to get? So it will be r double prime theta over r theta plus 1 over r. Then there's r prime theta over r theta plus 1 over r squared. Then numerator we have r theta double prime over r theta is equals to 0. 0 divided by anything is also 0. So this will cancel. Again, this will cancel. And even this one. So you can just say, or what we have is r double prime over r plus 1 over r prime over r plus 1 over r squared theta double prime over theta is equals to 0. So I can decide to take this one to the right. See, we are separating the variables, so those functions of r should be on one side and the functions of theta should be on the other side. So when I take it to the right hand side, what am I going to get? So this will give us or r double prime over r plus 1 over r prime over r is equals to negative 1 over r squared theta double prime over theta. But you see, on the right hand side, I only expect a functions of theta only. So I have to get rid of this 1 over r squared. So I'll multiply the whole of this equation by r squared. So both sides by r squared, so that you're going to say, therefore, you see, we are going to have r squared, that should be r, we'll have r squared times r double prime over r plus r squared over r is the same as r, then times r prime over r is equals to negative theta double prime over theta. And so the left hand side, I can see the denominator is common. So this simply means that we can write this as r squared r double prime plus r times r prime. This is over r capital is equals to negative theta double prime over theta. So this is our ODE after separating the variables. So these equations should be, because you see here, let me just remove what I've written there. Look at the left-hand side. This left-hand side, I can see it is simply a function of the small r. So this is a function of r only. What about the right-hand side? It's everything on the right-hand side. This one is a function of theta only. So the left-hand side is a function of r. The right-hand side is a function of theta. For them to be equal, then each side must be equal to a constant. Let's say the constant is k. So we are saying each of these sides must be equal to a constant k. K is a real constant. K is a real constant. Is a real number. K is a real number. So if I draw the number line, here we have negative infinity. Here we have positive infinity. Here we have 0. So k can be negative, k can be less than 0, k can be equal to 0, or k can be greater than 0. So those are the only three possibilities, because we are saying k is a real number. So we expect it to be less than 0, we expect it to be greater than 0, and also equal to 0. So that means we have three cases to consider depending on the value of k. So let's call this equation star. Now, case one is when k is, let me now start with positive. You see, usually when we are dealing with the equations in rectangular or Cartesian coordinates, we always start by saying when k is negative. But now when it is cylindrical coordinates, let's start with k, the case when k is positive, k greater than 0. So what happens? We say put k is equals to positive. Now I'm not going to use lambda squared. Instead of lambda, let me use n squared, where n is a natural number. So you can say where n is a natural number. So n belongs to the set of natural numbers. That's the set of all natural numbers. You see that means, it simply means n is equals to 1, 2, 3, etc. Natural numbers. Now, what happens? How will our equation look like? Equation star. So therefore, our equation star will now look like this. It will be, on the left-hand side, we have r squared, r double prime, plus r prime over r is equals to negative theta double prime over theta. Remember this capital theta. This equals to n squared. And if I multiply, not multiplying, but equate each of the equations by by n squared, what are we going to get? So, or the first one is r squared times r double prime plus r prime over r is equals to n squared, and negative theta double prime over theta is equals to n squared. That's what we have. So these are set of ODEs. So these two, they form set of ODEs. So we'll call this equation 1, and this one we call it equation 2. Now, let's start by solving equation 1. Equation Roman 1. It is this r squared times r double prime plus r prime is equals to n squared times r. I have multiplied both sides by r capital, of which if I rearrange this can as well be written as r squared. Remember, r double prime is the same as the second derivative of r with respect to the small r. So this can be written as d squared r over the r squared plus r This is the first derivative of r capital with respect to the small r. So dr capital, dr. Then I can now take this to the left-hand side. So it will be negative n squared times r. That should now give us 0. Now look at this equation. This is a second order ODE with the variable coefficients. How do we solve it? If you look at that equation, you realize that it is of the Cauchy-Euler type. So this is a Cauchy-Euler ODE. Remember Euler-Cauchy equations, the general form. So we solve it by making another substitution. So to solve this, you are going to say let r be equal to exponential t. Why are we making this substitution? Because this substitution will help us transform the ODE to that equation with variable coefficient. We are using this to transform it, to transform the ODE to an equation with variable coefficients. So you have to make that substitution. Now, how will the derivatives change under that transformation? You will find that upon transforming, you are going to get the derivatives to be this one, where we have r dr. This will give you dr dt. That is how you'll transform the second term on the right hand, on the left hand side. And where we have, let me write, I think this space is enough, where we have r squared, d squared r, and that should be d squared. Where we have r squared, d squared r, with respect to r squared, this should give us d squared r dt squared minus dr dt. Of course, the proof of how the derivatives transform to this manner, you saw that in ordinary differential equations. We don't need to derive this again. You see, as we proceed, you need to recall those concepts that you learned previously. So having known how to transform the derivatives, let's now see how will this equation look like. This one that I have ticked, that ODE. So therefore, our ODE will now be written as, use another color. It will now be d squared r dt squared minus dr dt. Then I can see the other one is plus dr dt, and then there's negative n squared r is equals to 0. So this was the first term, this one here. The other dr dt is for this second term. So when you simplify, you see this one and this will cancel. So what we have is, you can say, or d squared r dt squared minus n squared r is equals to 0. Or in terms of the d operator, if we say let our d operator be derivative with respect to t, so that the second, or d squared, will now be the second derivative with respect to t twice. So we can now write this equation in terms of the d operator. How will it look like? So this equation can now be written as, it will now be d squared r minus n squared r is equals to 0. Or if I factor out the r from the left-hand side, we'll have now d squared minus n squared. This should operate on the r capital to give us 0. Now we can now find the auxiliary equation, all the characteristic equations. We write auxiliary equation. So what is it? It is d squared, let me use another color, d squared minus n squared is equals to 0. So what are the roots? The roots of this equation, there will be 2, so make d the subject. So you're going to get d1 and 2, that means the first and the second root is simply the square root of n squared. And so this will give us what? Plus or minus n. So these are real and distinct. These roots are real and distinct. They are real and distinct. So then what happens? How do we write our solution corresponding to the R capital? So we are going to say that therefore, our R capital, which is now a function of t, remember, is equals to a constant, call it C1, exponential nt plus C2, exponential negative nt. How else can you write this? This can also be written as C1 exponential t, and this is raised to n, this is t, plus C2 exponential t raised to negative n. Remember, loss of indices. But now, what is exponential t? But we said, look at where we started with the substitution. Let me take you up. So we see the substitution. Where did we introduce t? It is here. In fact, we even bracketed it. So it means where there is exponential t, that should be equal to r, the small r. So I'll now go here and say that, but exponential t is equals to the small r. So therefore, this, or simply this implies that now our r, which is a function of r, will now be equal to C1 r raised to n plus C2 r raised to negative n, where C1 and C2 are arbitrary constants. So this is the solution corresponding to a capital R. That is equation Roman 1. Let us also solve equation Roman 2. What was it? We can go back and check. The one we called equation 2 was negative theta double prime over theta is equals to n squared. So I'll write here equation 2. Another color, you write equation 2. It is this one, negative theta double prime over theta is equals to n squared. So this equation, if I cross multiply, I'm going to get negative theta double prime is equals to n squared theta. Now, if I take this to the right-hand side, this can now be written as theta double prime plus n squared theta is equals to 0. Now, the prime here is now derivative with respect to the small theta. Take note. We can now write this in terms of the d operator. So you can just say let now the d operator in this case to be derivative with respect to theta. So this will imply that d squared will now be the second derivative with respect to theta twice. So this equation now in terms of the d operator, how can we write it? It will be d squared theta plus n squared theta is equals to 0, or d squared plus n squared operating on theta should give us 0. Again, we can find the auxiliary equation or the characteristic equation or the subsidiary equation. So let's write auxiliary equation. That is d squared plus n squared is equals to 0. Usually the auxiliary equation equate that d operator, the whole of that operator equate it to 0. Now what are the roots of this equation? The roots, we are going to say that, of course, there will be two roots, d1 and 2 will be the square root of negative n squared. So what will this be equal to? Remember, square root of a negative number is a complex number. So this will give us plus or minus iota times n. So the roots are complex conjugates. So these are complex conjugates. When you have complex conjugate roots, how do you write your general solution? So we are going to say that, therefore, the general solution, which is now theta capital, remember it is a function of the small theta, is equal to a constant, call it C3 cos n theta, plus another constant C4 sine n theta, where C3 and C4 are arbitrary constants. Now we know the two solutions, so we can now get the solution, the general solution of the given PDE. So our general solution that is of the PDE it will now be written as u of r theta. But I told you n is a natural number. There are so many of those n's. So it means we'll have so many of these solutions corresponding to the n's. So we can write this as u subscript n is equals to, remember it is r capital times theta capital. If I replace, our r was C1, then there's exponential n, let's just check. Our r was C1, r raised to n, not exponential. C1 times r raised to n plus C2 times r raised to negative n, and our theta we have found C3 cosine of n theta plus C4 sine of n theta. That's our solution. Remember, we are writing u subscript n because there are several of these n's. N is 1, 2, 3, etc. So let's apply the boundary condition. Apply the condition that u0r is finite, less than infinity. So what do we get? Remember, here we have un of r theta. So here can be u subscript n now because there are several of those u's. So u0r is finite. So what you're going to get here is that when I put r is equals to 0, what will I get? So this will be C1 times r raised to n, and our r is 0. So times 0 raised to n plus C2 times 0 raised to negative n times C3 cos n theta plus C4 sin n theta. This value should be less than infinity. It should be finite. Now look at here. This one can be written as C2 divided by 0 raised to n. That's how you can write it. And this one is C1 times 0, which is 0. So, and you know, anything divided by 0 should give us infinity. So it's like we are saying infinity times the whole of this other bracket is less than infinity. For that to be true, because we cannot say this is 0. If it is 0, then we are going to get a trivial solution. So for this to be true that our value must be finite, then we expect that C2 must be equal to 0. For the result to be finite, it must be 0 over 0. But if it is any other number, we are going to get infinity on the left-hand side. So this means that C2 must be equal to 0 for our result to be finite. Otherwise, for any other value of C2, we are going to get the result to be infinity. E.g., when you have 1 over 0, that is infinity. 2 over 0, infinity. But you know, 0 over 0, it means there's something common in the numerator and the denominator. So if you factorize, that can be simplified. If you are getting the limit and you realize that upon direct substitution, you're getting 0 over 0, you could use L'Hopital's rule or factorization to simplify what is common in the numerator and denominator so that you get your required limit. So we insist that C2 must be 0 for our solution to be finite. So let's go back and replace it here. I'm going to replace it here. So therefore, because now we have found C2 is equals to 0, our UN, U subscript n of r theta, is now equal to, we now remain with C1 times r raised to n times C3 cosine of n theta plus C4 sine of n theta. And this you can simplify. If I take C1 times C3, I'm going to get another constant. Also C1 times C4 will give me another constant. So let C1 times C3 be equal to A sub n, and let C1 times C4 be equal to B subscript n. So that this can now be written as r raised to n A subscript n cos n theta plus B subscript n sin n theta. That's what we have. Now, we have another boundary condition to apply. That is when R is equals to L. So let's apply that. Now, before we apply it, look at this solution. On the left-hand side, let me write or U subscript n of R theta. There are several of those U subscript n depending on the value of n. And remember, our solution of the given PDE should be U of R theta. So to get U of R theta, I must use what is called the principle of superposition. So we can write using the principle of superposition, principle of superposition. What does it mean? That if I need our solution U of R theta is simply equal to, of course, here we ought to have said that our n starts from 0. No, not 0. Our n starts from 1 all the way up to infinity. So this solution can now be written as, I will write the sum from n is equals to 1 to infinity. Then here we have r raised to n times a raised to n cosine of n theta, not b raised to that subscript, so b subscript n sine of n theta. In fact, I can put this in brackets, also this. So we are summing. Remember, usually u r theta is always equals to the sum of those eigenfunctions from n is equals to 1 to infinity of un of r theta. That is the principle of superposition. And if I replace the un of r theta, we get this equation that I've written down here, this one. So now, from that equation, now we can apply the other boundary condition. But you see, usually, there is that value corresponding to n is equals to 0. So we can cater for that in this equation even before we apply the boundary condition. So what we're going to do is to ensure that we account for the case where n is 0. So we are going to, let me rub this. Let me rub this here. I'm going to insert a certain term there corresponding to the case where n is 0. So this is, call it a naught over 2 plus. So this is u of r theta. Remember what we are saying is that you need to take note that u, when n is 0, as a function of r and theta, is the same as a naught over 2. So that when n is 1 to infinity, we have that summation. So that's very important. So let's apply the other condition. So you can write apply. The other condition, what was it? It was u L, when r is L, theta is equals to f of theta. So what do we get? That means you put r is equals to L, and your solution should be f of theta. So this is what you're going to get. So you can say therefore f of theta should be equal to a naught over 2. Remember, a naught is a constant, plus the sum from n is equals to 1 to infinity L raised to n a subscript n times cos theta, cos n theta I mean, plus b subscript n times sine n theta. Look at this one. This series, this is Fourier series of f of theta. This one is, let me bracket it. You remember we have three types of Fourier series: the complete Fourier series and the half-range Fourier series, which are two. We have half-range Fourier sine series and half-range Fourier cosine series. But now in this case, this is the complete Fourier series. Complete Fourier series of f of theta. So how do we find the Fourier coefficients? Recall from your calculus 4 that the Fourier coefficient a naught, of course this is valid in the interval. Our interval is from theta 0 to 2 pi. That's what we said. So theta is a member of that interval from 0 to 2 pi. So that here a naught will be 1 over pi. The integral from 0 to 2 pi of f of theta d theta. That's a naught. Another coefficient is a subscript n is equals to 1 over pi. The integral from 0 to 2 pi f of theta times cosine of n theta. Remember what you are calling this one. I should combine it with this because the whole of this is the coefficient of cos n theta. So I should have added here L raised to n. You pick the whole of that coefficient of cos n theta. That's what will give you that integral. So from here, you realize that if I make a subscript n the subject, I'll have 1 over L raised to n times pi. Again, the coefficient of sine n theta, it is bn times L raised to n. So we again write here that L raised to n times b raised to n, and not raised to, that's now subscript. B subscript n is now again equal to 1 over pi, the integral from 0 to 2 pi of f of theta, and I did not write here d theta, so let me insert it, d theta. F of theta, then there is now sine n theta, n theta, d theta. So these are the Fourier coefficients. So that if I want to find a n, you simply make it the subject. It is clear from there. So from here, it is clear that a subscript n is equals to 1 over pi times L raised to n. Integral from 0 to 2 pi f of theta times cosine of n theta d theta. Similarly, b subscript n is the same as 1 over pi times L raised to n, the integral from 0 to 2 pi f of theta times sine of n theta d theta. So that's what we have. Now, we now know the Fourier coefficients, and so we can now substitute them back to our solution, and that will be our general solution or the particular solution of the given PDE. So let's replace them in that equation that I have ticked. So you say therefore our particular solution, which is u of r theta, it is equals to n naught over 2. So that when you divide n naught by 2, you get 1 over 2 pi. The integral from 0 to 2 pi of f of theta d theta. Then plus that summation, we can see we have the sum from n is equals to 1 to infinity. Now, L raised to n times a sub n, we have it as this integral. So you see 1 over pi is a constant. So let me just write here. It is equals to 1 over pi times the integral from 0 to 2 pi f of theta cosine of n theta d theta. This is multiplying cos n theta. That's what we have. Then plus the other one is again, let me take this here. The other one again gave us another 1 over pi. The integral from 0 to 2 pi of f of theta sine n theta d theta. This is again multiplying sine n theta. So what we have there is our general solution that is corresponding to the first case where k is positive. Now, let me bracket this. So when k is positive, we are going to get this. Remember, we said we have 3 cases. So let's look at case 2. The other 2 cases are very short. Case 2. This is a case where k is equals to 0. So when k is equals to 0, what will we get? Equation star. Look at our equation side star. It was up there. Equation star. How will it become? It will become, let me use another color. It will become r squared times r double prime plus r, of course, the small r times the r prime over r capital is equals to negative theta double prime over theta, which is equals to 0, because now k is equals to 0. If I equate each side by 0, what are we going to get? So this will give us that r squared times r double prime plus r times r prime over r is equals to 0, and negative theta double prime over theta is also equals to 0. So what we have here is a set of ODEs. This is a set of ODEs. So we could call this equation 1, this other one equation 2. Let's solve equation 1. So right here, equation 1. If I cross multiply, I don't need to rewrite it again. If I cross multiply, I'll have r squared times r double prime plus r times r is equals to 0. I've cross multiplied. This is Cauchy-Euler. Again, this is Cauchy-Euler equation. You need to convert it to an ODE with the constant coefficients. Again, this is Cauchy-Euler ODE. So our substitution is that let r be equal to exponential t. So with this substitution, we are going to get where we have, remember here there was a prime correction. So where we have r squared, let's start with the first one, where we have r dr dr, that will now give us dr dt. Where we have r prime, that is the same as dr. Let me write this equation a better way. It is r squared d squared r with respect to r squared plus r dr dr. That should give us 0. That is the same equation instead of using the prime, so that you can see it in a better way. So the first derivative will transform in this manner. What about the second derivative? Where we have r squared d squared r dr squared, this will give you d squared r dt squared minus dr dt. That's what you need to get when you transform the second derivative. Again, you recall what you did in ODEs under Cauchy-Euler equations, how to transform an ODE with variable coefficients of the Cauchy-Euler type to an equation with constant coefficients. Now, when we substitute those derivatives here, what are we going to get? So our ODE should now give us, instead of this derivative, I'm going to write d squared r dt squared minus dr dt. What about the other derivative? It gave us again dr dt, so plus the other derivative gives you dr dt. And so that's what you have on the left. On the right, we have 0. So what do we realize? That this will cancel with this. So from here, we note that d squared r dt squared is equals to 0. So find r, integrate twice, so that you get your solution. So r as a function of t is equals to a constant c1 times t plus c2. The c1 and c2, this is c2. C1 and C2 are arbitrary constants, but we need to replace t. What is t? Because we need to go back to a function of the small r. So from here, you realize that the natural log of r is equals to t. So where there is t, you put ln r. So therefore, r now as a function of the small r, it will now be equal to C1 times ln r, then plus C2. I have replaced t by ln r. So the t will give us ln r. So that's our solution for the first equation. Let's also solve the second equation. Equation Roman 2. In equation Roman 2, how do we solve it? Let me write it here. It was negative theta double prime over theta is equals to 0. And if you cross multiply, we are going to get theta double prime, you cross multiply and simplify, is equals to 0, of which if you integrate twice, you're going to get theta as a function of theta, remember, is equals to, call it C3 theta plus C4. C1, C2, C3, and C4 are arbitrary constants. So with those, we can now find our general solution corresponding to those to r and theta, or simply as a function of r and theta. So you can just say that therefore, or let me say hence, and this is better than therefore, hence, our solution u of r theta is equals to, so we have the first one, remember it was r times theta. So when I replace r, I'm going to get C1 ln r plus C2. And when I replace theta, I'm going to get C3 theta plus C4. Now, let's apply the first condition. The first condition is that the solution should be finite when r approaches 0. So let's apply this. I can use another color. Apply. Our condition is that u of 0 theta is a value less than infinity. It is finite. So what do we get? Put r is equals to 0. So we are going to get C1 ln 0, ln of 0, plus C2. Then times the other one, C3 theta plus C4. The value we get here should be less than infinity. Now, something very important. What is the natural log of 0? Natural log of 0 is infinity. C1 times infinity is infinity, plus any other thing is infinity. And infinity times any other value is still infinity. On the left-hand side, we have infinity. On the right-hand side, we have less than. For this equation to be true, if you want to kill the infinity that is affecting our left-hand side, you must ensure that C1 is 0, so that we kill that infinity, because we expect our left-hand side to be finite, a value less than infinity. So for us to kill the ln 0, we must ensure that C1 is equals to 0. So therefore, C1 must be equal to 0 for our solution to be finite. I hope that is taken home. So therefore, if we now replace it here, what will we get? If we replace it there, you can just say that therefore, our u of r theta is equals to, now it is now C2, because C1 is 0, C2 times C3 theta plus C4. That's what we have. And you realize that if we take the C2 inside, because we can simplify this equation, C2 will multiply C3 and C4. So you can just say, or u of r theta is equals to, let's now call it A capital times theta plus B, where A is C2 times C3 and B is C2 times C4. We have another boundary condition to apply. Another boundary condition is when R is equals to L. But you see on the right hand side, we don't have R. It's simply a function of theta. So what can we say? We cannot even apply the other boundary condition. Now, this is the question you need to ask yourself. Is this solution periodic? This is not a periodic solution. This one is not a periodic solution. Remember, when you are dealing with the method of separation of variables, usually our task is to find a solution which is periodic and non-trivial. Those are the two things that you need to look for. Are you able to find a non-trivial solution? That's the first question. Another question, is that solution that you have found periodic? If not, then it is not a solution that is of interest to us. So this solution is not of interest to us. Why? Because it is not periodic. I hope that is answered. Now, let's look at another case. So before we look at the other case, let me explain what you mean by periodic solution. It is a solution that is in terms of sine and cosine. That is the solution that we are interested in. So we expect that for this solution to be periodic, for it to be periodic, then A must be equal to 0. For that solution to be periodic, A must be equal to 0. So that will give us, therefore, that U, let me use another color. I don't need to write so many things because that will take a lot of our time. So we have just explained here that if you want your solution to be periodic with period 2 pi, then A must be equal to 0. So this means that our solution, which is U of R theta, is now equal to a constant B. If I replace B by another constant, because this is just a constant, if I replace B by N naught over 2 is still another constant. And you see this is the solution corresponding to the case when N is equals to 0. So we get here that therefore U naught as a function of R theta should be equal to a constant a naught over 2. So somebody was wondering, why did we have a naught over 2 in case 1? This is where we got it from. That's where we got it from. And that explains why, let me take you back. That explains why I was adding a naught over 2 to this solution. This was the one corresponding to n is equals to 0. You see, we even wrote it here. So that question has now been answered, and that's where we added it to this principle of superposition. Having applied that principle, we also added that solution. For the case where n is 0, or when n is 0, k is also 0. So we got it from case 2. Now let's go to case 3, the last one. Now you know what is happening. I'll not take a lot of time explaining how to solve the equations in case 3. So we can write here that in case 3, let me write here case 3. So in case 3 is the case where we expect k to be less than 0. So you write case 3. It's taking quite a longer time. Can add that. That is case 3. So this is the case where k is less than 0. And in particular, we are going to put k is equals to, now it is negative of n squared. Where n is not equal to 0, n is a natural number. Where n belongs to the set of natural numbers. Remember, natural numbers, we have 1, 2, 3. So this means n is equals to 1, 2, 3, and so many other terms. So what happens to our equation star? Let's write it here. Our equation star can now be written as, can use another color, that r squared times r double prime plus r times r, everything over, remember this is r prime, everything over r is equals to negative theta double prime over theta, which is equals to our k, which is negative n squared. And from this one, you can get a set of 2 ODEs. So you can just write odd r squared times r double prime plus r times r prime over r is equals to a negative n squared, and the other one is negative theta double prime, that's capital theta, over theta is equals to negative n squared. So one of them is equation 1, another one is equation 2. So we call this equation 1 the first ODE, the other one is the second ODE. So these two equations are they are a set of ODEs. So let's solve equation 1. Now I'm going to be very fast because now we know everything that entails the solution of this kind of equations. Equation 1, you can of course multiply and then rearrange it. How else can it be written? It will be written as r squared times r double prime plus r times r prime plus n squared times r is equals to 0. I have cross multiplied and then rearranged to get that equation. This equation is called Cauchy-Euler equation. Let me write it explicitly without using the primes. This equation can be written as r squared d squared r with respect to dr squared plus r dr with respect to r plus n squared r. That should be able to give us 0. So this Cauchy-Euler, I talked of Cauchy-Euler, let me explain it here. Cauchy-Euler ODE. So how will we transform this derivative? Of course, you start by saying let, where we have r, let it be equal to exponential t. That's the substitution. We need to transform it to an equation with constant coefficients. So how will this derivative transform? This will give us d squared r dt squared minus dr dt. That's the second derivative. Then plus, what about this other derivative? That will give us dr dt. So that is dr dt, let me write here dt, plus n squared. Remember now the r here is a function of t is equals to 0. And you can now simplify. This will cancel with this. So I only have d squared r dt squared and then plus n squared r. So this therefore means that, let me write it here, that d squared r dt squared plus n squared r is equals to 0. Now you can write this in terms of the d operator. In terms of the d operator, let me just see something here. A correction here. This was equation 1, not star. This one. This equation Roman 1. That's what we are solving. So this equation in terms of the d operator can now be written as d squared plus n squared operating on r to give us 0. And so what is the solution? Of course, the auxiliary equation, you don't need to write so many things now. Auxiliary equation will be d squared. Let me just write in the short form, auxiliary equation d squared, that should be d squared plus n squared is equals to 0. What about the roots? Make d the subject. So you see d1 and 2 will be the square root of negative n squared. d1 and 2 is the square root of negative n squared. That will give us plus or minus in. where I is a complex number, which is the square root of -1. So this is the same as I times n. These are complex conjugate roots. So therefore, the solution corresponding to R in this case is, remember, R is a function of t. It will be equal to, call it C1 cos nt plus C2 sin nt. So that's what we have as our solution corresponding to the capital R. How else can we write this solution? That is the question that we need to ask ourselves. If we treat this as real, if we treat the roots as real and distinct, this solution can also be written as, another way of writing it is C1 we could write the solution as C1 times. So let's just leave it as that one, but we now need to replace t. So I'm going to just wrap what I've written here. Let's leave it as C1 cos nt plus C2 times sine nt. Now, if I replace t, remember where there's t, that is ln r. So we put t is equals to ln r from here. Our t, or simply when you take natural log on both sides, so ln r is equals to t. Very important. So therefore, that r as a function of r can now be written as C1 times cosine of n ln r plus C2 times sine of n ln r. That's what we have as the solution for the first equation. Let's see how to solve the second equation. We have theta double prime over theta, of course negative, is equals to negative n squared. So we're going to write the equation 2. I'll do it down here. That is now the solution for equation 2. Equation Roman 2. Which equation is this one? It is negative theta double prime over theta is equals to negative n squared. And if you arrange this equation, we are going to get, of course, across multiply by theta, then I take everything to the right-hand side. We are going to get theta double prime minus n squared. This should be n. Let me write that in a proper way. Minus n squared theta is equals to 0. And so in terms of the d operator, we are going to get d squared minus n squared operating on theta to give us 0. What is the auxiliary equation? In this case now, remember now the d in this case is derivative with respect to the small theta. So that our auxiliary equation is d squared minus n squared is equals to 0. So the roots, you make d the subject. So the roots here is that d, of course there are two roots, d1 and 2, is the square root of n, which is either plus or minus n. Now in this case, the roots are real and distinct. So how do we write our general solution corresponding to theta? So in this case here, theta, which is a function of theta, is now equal to C3 exponential n theta plus C4 exponential negative n theta. That's what we have as our solution for the other variable, theta capital, where C3 and C4 are arbitrary constants. So what about the general solution? So we can just say hence, now we need the general solution of the PDE. Hence, our u as a function of r and theta is now equal to, remember it was r capital times theta capital. Let's multiply them. Our r capital was C1 cosine of n times ln r plus C2 sine of n times ln r. That's our r capital. Now, the theta is C3 exponential n theta plus C4 exponential negative n theta. But you see, n, these n's are so many, so I can just write here, or u substitute n of r theta. Why u sub, this is r theta. Let me write before I explain. Of r theta. Why am I saying u substitute n? Because these are the eigenfunctions, because there are so many n's, and so even those eigenfunctions are so many depending on the number of the n. So that's why we have u substitute n to be equal to that. And now we can apply the other condition. Remember, we are told the solution approaches 0 when r approaches, the solution is finite, I mean, when r approaches 0. So let's apply this. Apply. The condition is that un of 0 theta is less than infinity. So what are we going to get? When you put r is equals to 0 in this equation, we are going to get C1 cosine of n ln 0, n times infinity. Or simply, remember ln 0 is infinity. I'll just write cosine of n times infinity plus C2 sine of n times infinity, because here we have ln 0, which is infinity. Again, here it is infinity. So this is a multiplication. Then here we have C3 exponential n theta. It is only r that we are replacing, plus C4 exponential negative n, that should be n, negative n theta. This value should be less than infinity. It should be a real number. It should be finite. For it to be finite, look at here. Let me ask you, what is cosine of a very, very big number? And what is sine of a very, very big number? We can press in our calculator. For instance, we can try, let's say cos. Let's say we are saying of 1 million. Cos of 1 million, it exists. What about sine of 1 million? We can again press sine of 1 million. It exists. So that value is finite. Now, what about 1 billion? Cos of maybe 1 billion. What do you get? The value exists when theta is very big. And what about sine of 1 billion? The results exist. So what can we say? For that value to be less than infinity, because I can't see where we have infinity on the left-hand side, so this condition cannot give us the values of C1, C2, C3, and C4. It cannot give us those values. So that condition fails to give us the values of interest. Let's apply the other condition. Apply the other condition is that u subscript n L theta is equals to f of theta. Now, before I apply that condition, you can use the principle of superposition to combine these things as a summation. So, using the principle of superposition, this is what we'll have. Of superposition. What are we going to get? We're going to get u of xt, not xt, that should be r theta, is equals to, now remember this, that corresponding to, just call it a naught over 2 plus the sum. The sum from n is equals to 1 to infinity of what we have there, of the u subscript n of r theta. U subscript n of r theta. So I'm going to write it. That is C1 cos n ln r plus C2 sin n ln r, that will be n, sin n ln r then I can see this times C3 exponential n theta plus C4 exponential negative n theta. So when I apply the condition at r is equals to L, this one, we expect to find f of theta. So therefore, f of theta should be equal to n naught over 2 plus the sum from n is equals to 1 to infinity. Then here we have C1 cosine n ln L plus C2 sine of n ln L times C3 exponential n theta plus C4 exponential negative n theta. Now, this thing here is not periodic. If you look at that solution, it is not periodic in the variable theta. So therefore we say that it is a solution of no interest to us. Look at this. Because you cannot say that this Fourier series must be periodic in theta. But this one, it is not Fourier series because here, there's no theta here, neither do we have the theta here. So it is not periodic. So we say this solution that we are talking about is not periodic in theta, and therefore it is of no interest to us. So then what it means that what we got in case 2 and case 3 are not of interest to us. The only solution that is of interest to us is the one that we got in case 1. Let me check. The one that we got in case 1 is now the required solution. It is the solution that is periodic in theta, and so it is also non-trivial. So therefore we go for this solution. It is a solution that has physical significance. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. If you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to like, comment, and share this video. When we meet next time, we look at other problems in partial differential equations. Bye-bye.